But then certain people, like, they couldn't stand it. So
I feel like I'd be the one that couldn't stand it.
I probably would be as well. All right, let's get started. Let's settle down and get back into the world of reinforced concrete design. That was a good one. This isn't soils. We don't settle in here. I didn't come up with it. He did. He did.
That's solid. I like that. Spicy. We don't have weight of solids.
All right.
We're a very diverse campus.
Okay. A couple things. So you all have homework 7 due on Monday. I did want to give you a point of clarification so that you were able to attack problem 2. If you look at problem 2 is a doubly reinforced section. I don't think it's that section. I just pulled a section to sort of clarify what's going on. When you do a transformed section analysis, let's say that upper layer of rebar isn't there, okay? Because if all you have is just the concrete in the lower area of, or the lower pieces of rebar, then you would say, okay, everything below the neutral axis is in tension and it's ineffective. So you have this lump of concrete, and then you have, or on the bottom, you have the steel converted into concrete through the modular ratio. So on the bottom, the area is just NAS. Sound good? Technically, you should do the same thing for the top layer of steel, so it would be NAS prime. However, if you just did NAS prime, you'd actually be double counting this area where the bars are. So the way that we handle that is we turn this into an effective lump of concrete with NAS, but on the top, we turn it into an effective lump with N-1 AS prime. What's that? Okay, so no. Here, what I'm trying to get at is this. Okay, let me see if can I draw on this? Yep. Okay, so here's the concrete, right? All right, so here's the bars, right? So what we would do is this. Okay, so you've got area right here, right? Sound good? All right, so you would remove that area and then replace it with an effective lump of concrete, right? Sound good? All right. So essentially you've got like a little lump of concrete sort of right here, right? But you've already filled in these circles right here. So all I'm saying is that because you've already got this concrete here, you have, NAS, the lump of concrete, NAS prime, but because you've already filled these in, you technically need to take off one more AS prime, so you're not double counting that area. Do you see what I mean? That's why I'm saying N-1 AS prime. That's all that is. Now, one thing let me point out, and let me say this. If you read the book is going to say 2N-1 times AS prime. I think there's a little bit of conflict or conflicting viewpoints about that in the concrete industry. They like to include the 2 for the fact that you get creep in the compression regions of the concrete. Personally, I don't. That 2 was used more, I guess, back in the day when we had working stress methodologies, so I don't do that. And honestly, I don't think it's going to affect your answer that much anyways. So for tensile steel, just use NAS, and for compression steel, N-1 AS. Yes, sir?
So you're subtracting like just one of the bars, right? And say like that would be assuming that that section in the middle is half of the...
No. Okay. All right. Here's what we're doing. Okay. All right. I think we're probably making this too complicated. So here's what it originally looked like. Okay. And we've got a bar here, and let's say a bar here. Sound good? Everybody okay with that? Now, what is the area of the concrete? This is B, and then that's what, X, right? Okay. Now, if I turn this steel into an effective lump of concrete, essentially what I'm doing is I'm removing that steel here and here. So the actual concrete is this area here. This is the area of the concrete. And my point is that you've got these two sort of voids right here that you're replacing with steel. So before, the area of that lump of concrete was B times X. Here it's not. It's BX minus whatever that area of steel is. Does that make sense? That's why I'm saying you got to have that subtraction. Does that make sense? I mean, I'm just saying we're not going to double count. Everybody okay with this? I feel like this is confusing everybody a little bit.
So we're just removing the rebar and we're counting it as a form of effective concrete.
That's it. Yeah.
That's all we're doing.
Yeah. Yeah.
Okay.
I'm just trying to make sure we're not double counting. We're not accounting for the same area twice. That's all I'm doing. Everybody okay with that? Okay. All right. Okay. All right. Does everybody remember the schedule for the exam? We turn in our homework on Monday. I'm not accepting late homework because I'm giving you the solution that day. So if I don't have it on Monday, that's it, because I'm giving you the solution. Sound good? We have our celebration on Wednesday. We'll start at 9:55. I assume that you all, again, don't have any time conflicts, so you don't mind if we go till 11:30? We handled that before, didn't we? Because that's what we did last time. So I don't think anything would change. Am I right? You sh- well, this is Wednesday. Okay, all right.
Take a long time to get
Good. Everybody else good? Okay, all right. And the sign-in sheet's going around, right? Yeah. Okay, all right. So let's get into development link. What I want to do today is do some example problems to illustrate development link. And again, I think you're going to find this is really simple. Okay, so let me start off with this. So I think by now, we've well covered the concept of bar development, the idea that you must embed a piece of bar a certain depth within the concrete to fully develop its capacity. The empirical expression that we use in ACI is the following. I know it looks long. Ultimately, it's pretty straightforward. Once you figure out all of your constants, it really is just plug and chug. So we have our material parameters, our Fy, our Fc prime, our lambda factors. We have our adjustment factors, psi sub t, psi sub e, psi sub s, based on different facets related to the reinforcement. Do they have epoxy coating? How big are the bars, etc.? And we also have the spacing limits based on transverse reinforcement, how far apart that's spaced, distances to the edge of the beam for cover requirements, etc. So we have our reinforcement location factor, bar coating factor for epoxy coated bars, and we have reinforcement size factor. Pretty straightforward. Okay, our spacing and cover requirements, again, capped off, that ratio is capped off at a maximum of 2.5. Everybody good? Everybody good? Okay. That ratio is capped off at 2.5. It's also a function of your transverse reinforcement index. For our first calculation, we're going to assume that's 0, and then we're going to take into account transverse reinforcement and see how much benefit do we get from actually accounting for it. Couple minor provisions. Make sure that your psi sub t and your psi sub e, when you multiply that, is always less than or equal to 1.7. That's just an upper limit so that you don't get answers that are a little weird. And you can also reduce your required development length based on the ratio of how much steel you provided versus how much you need. Okay, so if you need 3 square inches for capacity and you provide 6 square inches, well, you don't need as much development length. You only really need half as much because the theory is that the bars are only going to be seeing half as much force. So that's basically it. Okay, so here's our beam. We're going to determine the development length using KTR equals 0, and KTR is computed. Now for this problem, we have 3 KSI normal weight concrete. So remember that means your lambda value is 1. We've got an FY value of 60 KSI. Some other important parameters. We know our stirrups are number 3s and they're spaced at 8 inches. Let's see if you all remember pop quiz. If I have number 3 U-shaped stirrups, what's the area of steel? 0.22, right? The area of a number 3 bar is 0.11 square inches. 2 of those is 0.22. Y'all remember that? Well, you all have a celebration on that next Wednesday, so I hope you remember it. What's that? All right. Our bars are, now here's one thing to point out. Our bars are 2.5 inches from the edge, from the side edges of the beam. They're 3 inches from the bottom edge of the beam, and they're 3 inches from each other. So that's going to be important when we determine our C sub B. Okay? Sound good? All right. So let's take this one at a time. We have 3 number 8 uncoated bars. So let's get some parameters. So close that. Whoop. Close that. All right, so material parameters. So we have FC prime, 3 KSI. It's 3, right? Make sure everybody's paying attention. Everybody good? Okay. What was lambda? There we go. And we have a FY of 60. Okay, now, if we have number 8 bars, so we'll say bar size. If we have number 8 bars, what is the diameter of a bar? What's that? What'd you say? Do you need to look that one up? 1 inch. Anything from a number 3 to a number 8, your diameter is that number divided by 8. So if it was a number 7 bar, your diameter would be 7/8. If it was a number 6 bar, your diameter would be 6/8 or 3/4. So a number 8 bar, the diameter is 1 inch. Now don't get that confused with a number 9 bar where the area is 1 square inch. There's a difference between diameter and area. So, sound good? All right. Y'all should remember that. Okay. Now our adjustment factors. Okay, this involves going into the code, or in this case you can go into the slides, and we're going to take each one of these one at a time. So let's start off with psi sub t. What is psi sub t going to be for this beam? I want everybody to understand this. I'm making you all look it up. What? Which one? You say 1. That is correct. The easiest way to recognize that is because these bars are on the bottom. And everybody knows which bars we're trying to compute the development length for, right? It's the bars on the bottom of the beam. Everybody okay with that? Okay. So that's psi sub t. What is psi sub e? And why is that? They're uncoded. Top bar factor and epoxy coating factor. Remember that? All right, now, I'll go ahead and do this now. What is psi sub t times psi sub e equal to? 1. And that needs to be less than 1.7. If it's greater, then we just take it to be 1.7. Okay? Sound good?
Why are we only including the development
That's what we're trying to do.
Oh, wait. Oh, man. Am I? Yeah, never mind. I was remembering the example that we talked about before we started with the
That comes next. That comes next. Now, what were you saying? Did you have a question? Yeah. Oh, I'm sorry. Okay, I'm sorry. Now, our reinforcement size factor, what is that? 1. Why is that? So we'll say bigger. Bigger than number 6. Okay. Now C sub B. C sub B is one of 3 potential values, right? So let's go back to the slide that defined C sub B. I'm on slide 236. Now C sub B can either be the side-to-side distance, the distance to the top or the bottom, or half the center spacing between each bar. So let's just do this mentally. C sub B 1 from the bar to the sides of the beam is what? 2.5, right? From the bar to, let's say, the bottom of the beam, what is that? 3. From the bar halfway over to the next bar, what is that? 1.5, right? Because they're spaced at 4 inches. Or 3 inches, sorry, 3 inches. So if you've got 2.5, 3, and 1.5, what do you think mathematically is going to be the most conservative answer? 1.5, okay? Remember, that distance is telling you how much concrete will resist that bond crack. The smaller answer means the least amount of concrete. Okay, so I'm saying this is 1.5. And also, mathematically, that works as well. C sub B is on the bottom of the fraction. So the smaller that answer, the larger the development length. I think the worst case scenario is that you need more development length. So that's why that's on the bottom. Does that make sense? Okay. Now, KTR for now is 0. Now, KTR actually is units of inches, so we're going to say that's 0 inches. We're going to deal with KTR being 0 now, then we're going to change it later. Okay? Sound good? Now, while I'm at it, let me also make another check. CB plus KTR over the bar diameter is, what is that? What's that equal? 1.5? Is that good? Why? It needs to be less than 2.5. If it's greater than 2.5, we just use 2.5 in our expression, just like up here. If that value is larger than 1.7, we just use the 1.7. Sound good? This is simple. Therefore, our development length, oh, it got tangled up. Our development length is 3 over 40 Fy over lambda square root of Fc prime times, let's see on the bottom, CB, bless you, KTR over dB. Then we have psi t, psi e, psi s, then all of that dB. I know that looks complicated, but in actuality, it really isn't. It's really just one big fraction, okay? Let's just deal with all the stuff on the top. Actually, no. Let's do all the stuff on the bottom first. On the bottom. So we have 40 times lambda. What's lambda? Square root of Fc prime? Square root of? There we go. And then, now what's this stuff in the parentheses equal to? We just did that. All right? Now on top, what do we have? We've got 3, bless you, times, what's Fy? There we go, 60,000 psi. Remember, got to have consistent units. All right? What are each of these factors? And what's our bar diameter? So, what do we got? Say it again. 54. We'll just keep it to like 54.8 or something like it. Now, 54.8. Do I have a second on that? What are the units? Even though I kind of ruined it. Inches. It's inches. And here's why. Nothing in this fraction has units other than psi and psi, which cancels, and then this. So
It's not empirical?
well, the equation's empirical, but the units work out. That is true.
Not at all.
Any questions? Now, let's see what happens if we compute that, that KTR. All right. Now, KTR is 40 ATR over S times N. Okay? Now, clean that up a little bit. Now, let's take each of these one at a time. Okay, what's ATR? 0.11. 0.22. Now, why is it 0.22? It's a number 3 U-shaped stirrup, right? You cut through 2 of them, exactly. Right? Everybody remember that? Now, how many bars are on a single layer? How many longitudinal bars are we dealing with? Bars running along the beam. Yeah. How many of these are there? 3. Okay? Whoa, what happened there? Now, what is S? S is your stirrup spacing, which is, so, you tell me, is it?
Is that including 2 inches from the start?
No, we're just, that 2 inches is just to get our pattern started. It doesn't really, we're not really using that for a transverse reinforcement spacing, yes. What's that? Well, what I would do is this. All right, look, think about what we're using this for, okay? We're using this transverse reinforcement index to recognize that those stirrups are confining the concrete, right? So we get a benefit from that, okay? So let me ask you this. Let's say we're at a transition region and we're trying to compute development length like right here. And on this side we have 8-inch stirrup spacing, and on this side we have 12-inch stirrup spacing. On the side of conservatism, what would you use? Oh, use a 12. Yep. That and larger stirrup spacing provides less confinement. So just be conservative. So if we were talking about the start of the beam, I mean, yeah, you could use the 2 inches, but to be conservative, I mean, that 2 inches is just to get the stirrup layout started. I would just go with the 8. So, make sense? All right. So what do we got for this? Say it again. 0.367 what? Inches. Man, I'm staying out of this and just going to talk about let's talk about this CB plus KTR over DB. Let's talk about this. What do we get for this? I mean, do I need to plug and chug, or can you all just do that one? So what do we got? Well, what's DB? So we're not dividing by anything, so there you go, there you go. Is that okay? What's it got to be less than? There we go. So now we can compute a new development length that accounts for transverse reinforcement. I can do better than that. Of course, you all are going to have to memorize this equation on the exam. No, it's not all you have to do. So what do we get for this? I mean, do I need to plug and chug, or are you all good? I mean, really, we're just replacing the 1.5 with the 1.867. So. .00 inches. Do I have a second on that? So therefore, your development length is 54.8 inches or 44.0 inches, depending upon whether or not you use KTR. Now, I'm telling you in cases where you know you're going to want to use KTR. I just wanted to expose you to the constants one at a time. Like we'll start off with KTR equals 0, and then we'll handle it. I didn't want to throw all the details at you all at once. I wanted to take it one step at a time. So this is KTR equals 0. KTR doesn't equal 0. So, hold on. If you've got, so let's be clear about what's going on. If you've got this beam and you are expecting that it can reach its full capacity right here, like right here at this section, well then you need to make sure that those pieces of bars, like these 3 number 8s, are embedded into whatever concrete they're adjacent to, a total distance of 44 inches. So that's your development length. Oh, he was first, and then, yes. You'll know. You got to read the problem, but you'll know. We'll get to that.
And also, what if there's, the column that's framing into whatever?
We'll get to that, and that's where hooks come into play. That's where hooks come into play, and we will get to that. We'll get there. Yeah. Now let me explain where that if you want a concrete example of where that comes into play. All right. Remember this? Do you remember this example? Okay. Let's go back to this example because I want you to understand the theory. So I've been getting questions about, well, what if you don't have 44 inches of development? Well, let's take what's going on with this. I really want to focus on this 6'9" bar right here. Okay, so this 6'9" bar right here. Do you remember why we cut it off right here? Do y'all remember that? Okay, let me go back to the discussion so that everybody remembers. So we had a beam like this, and we said, okay, here's the beam, and here's the reinforcement. Okay, so we said, all right, that beam has a maximum moment of about 618.75 foot kips, and then we put 6 number 9s in it. That'll give us a capacity of 623. And that's great and everything, but we don't need that reinforcement everywhere because right here we've got very, very low moments. Sounds good? Okay. In other words, if we go through and interpolate off our moment diagram, we really only need 6 bars about right here. We need 4 bars about right here and 2 bars about right here. Sound good? Okay. What I'm saying is at this point right here, that is where you need those 6 bars. But you cannot theoretically cut it off right here because these bars have to trail in to the concrete a little bit. How far do they need to trail in? Well, I'm going to say about 44 inches if we were talking about the same beam. Okay? Does that make sense? What I'm saying is that at this point right there, that's where we need to be able to develop the full capacity of those bars. That doesn't mean we cut them off right there. We cut them off at their development length. Does that make sense? Everybody okay with that? Now, I might be answering your question here in a second, but bear with me. What about right here where you don't have 44 inches? Well, you have 2 options. Number 1, if you have a column these are framing into, make sure that you can embed into that column, or you're going to need more bars over there. You're going to need more bars right here. Like you see how at this section we've got only 4 bars? You might need more of them. Even though from capacity standpoint you're good, you got to be able to develop those bars. So, is what it is. Was that what you were going to ask? Yeah, I had a feeling so. But that's what I'm getting at. What if it was 44 inches? That is only. Yeah, that's what we're talking about. Say, what if that's sort of what he was, I guess, going to ask. Let's say your development length is 44 inches. That's not 44 inches right there. That's only 3'1". So what I'm saying is at that section, you would probably need to take those bars out past the beam and embed them in some column, or you might need more reinforcement there just for that very fact. Now, you could also, ooh, this is going to test my 3D art skills. You could increase the number of stirrups right there. There we go. Oh, we're getting into some critical thinking stuff. I like it. Yes, it was. Yes, it was. Okay, if you're cutting off those bars like right here and you realize you don't have enough room, maybe hook them. You know, by hooking them, you get an added, benefit. Does that make sense? Everybody okay with that? But
Original bar doesn't create any development.
what's that?
Like where you cut it off at 6.9 feet.
Yeah, this way, not that way. Because think about what would happen if you apply a moment. Let's just keep it simple. If you apply a moment to a beam, you're taking it and you're doing that. You're bending both sides. So remember, you cut a section, you get the same moment on either side. It all goes back to that cantilever. If you had that cantilevered beam, and you needed that bar development right there, yeah, you've got the beam fully cast into the beam. It doesn't matter because you haven't developed it on this side. So, that's a good point, though. Make sense? Anybody got any questions about this? Yes.
So, to design a beam, first we have to find how many bars we need, then where we need them, and then the development length for each one, and if not enough, then it comes.
Yep. Yep. I didn't want to do that all at once. I wanted to take it a little bit at a time throughout the semester, because if I do it all at once, it hits you like a bucket of water. So that's why we take it a step at a time. You like that? Just like that? Well, that would hurt.
How would this work if you're recasting beams? You had to develop them?
Are you talking about the pre-stressing strands?
No, like if you had them used to develop, like would you just always have to hook them if you were, like we said at the parking garage, how they were bringing in the bait in order to precast it?
Oh, okay. Number one, they're more than likely using these types of elements. Depending upon the element that we're talking about, sometimes they leave a little bit of reinforcement exposed and then they cast on top of that. To give you an example, I know it's not a precast element, but I think it's a very good visual example of what we're talking about. Have you all ever seen like DOH bridge construction where they're casting, let's say, the concrete deck, and they cast the deck, but right there at the ends they leave like loops sticking out or little pieces of rebar sticking out on the ends? Why do they do that? No, I'm talking about at the, like, here's the bridge. All right. I'm talking about here's the bridge. Here's the beams. And I'm talking about right here. Why do they leave little pieces of rebar sticking out right here? Exactly, the barriers. They're going to come in and cast a concrete barrier right here. So in order to make that integral with the deck, they have to leave some bars exposed. Well, how far do they expose them? Their development length. So, see? All comes together, right? All right. Does this make sense? I really want this to make sense. I mean, this is a simple topic, but a lot of times it's not covered, so I think it's important. So, everybody good? Yes.
So, are the hooks exposed to, why are they?
They're only out there like for like a couple, or theoretically they'd only be exposed for a couple days. Like they would, if they had some precast deck they were dropping in, they'd drop the deck in, grout it up, and be done, and then cast the parapets right then, maybe like slip form them or something like that. So hopefully they're not sitting out there for years, because hopefully the DOH finishes the bridge. But let's move on. Yes, sir.
This might be a big question, but if you're talking about structure that's precast, do you ever see threaded rods inserted in the concrete to help cast it together? Not threaded.
You see pre-stressing strands that, like, you'll have some precast element that has like a duct through it. Like they'll use something like PVC or something to create a duct, or some tubing or some conduit. Then they pass strands through it and jack it together. Now that's a post-tension pre-stress system. It's not threaded rod, but it's kind of what you're talking about, I guess. Not really what you're talking about, though. Now, I'll say this. When you're casting abutments, for bridges, they sometimes leave threaded rods for beam seats. Like they'll set the beam down, and then, they'll have some slotted hole, let's say, in the plate, and then they thread that on, as an expansion joint. But not to, like, put a structure together, I think, like what you're talking about. I don't think that's done very commonly. Anything's possible, but anything else? This is good stuff. All right. Okay. Let's do another one. All right. So first off, let me erase all this. Okay, so we did 16A, right? So let's do 16B. Now, I've got 4 uncoated bars on this example. A couple things are a little different. Now, I was nice on this one. I gave you the lambda factor. I almost wanted to make you all look it up, like, because it's lightweight concrete. How about this? If it's sand lightweight concrete, what's the lambda value? 25. There we go. There we go. Oh, because otherwise, like, we don't remember that. That's right, I did, didn't I? Yeah. Okay, now, we have 4 number 8s. We have KTR is 0. KTR is computed again. Want to make sure everybody's comfortable with all that. 3.5 KSI, 60 KSI steel. When we designed the beam, when we did our design calcs, we said we needed 2.88 square inches of steel. Now, what we ended up doing is going into the manual and finding the next best, or in the manual, in the charts, whatever, and finding the next best option, which was 4 number 8s of 3.14 square inches. In other words, we provided more steel in the beam than we needed. I mean, not a lot more, but we did provide a little bit more. So 2.88 square inches versus 3.14. So we're going to be able to reduce our development length a little bit because of that difference. Sound good? So let's get into this. All right. Come on. We're not going to be able to finish it, but is it 16? 16B? So we'll just say general beam parameters. So all right. All right. I'm going to call this area of steel required was 2.88 square inches, but our actual area of steel is 3.14. Come on, I can do better than that. What's that? Pi, yeah, basically. All right, now, what's our bar diameter? Huh? 1 inch. Because we're dealing with a number 8. Now, our adjustment factors. I want to get ahead of myself. Let's take them one at a time. What's psi t equal to? Say it again. It's 1.3. The easy way to describe why is because those are top bars. Okay? What is psi sub e? 1. Uncoded. All right? On the side, what is psi t psi e equal to? That's less than 1.7, so we're okay. What is psi s? Because we're dealing with number 8 bars. Okay? Now, can somebody tell me what the C sub B value is for this beam? 2 inches. I think I heard a couple people say that, so I got a second on that. All right, good. All right, so here's what we're going to do. I think I'm actually going to call it today because I do want to take a little bit of time and go into the reduction and how KTR affects it and what have you. So let me say this, okay, so everybody's clear on it. I mean, here's the slide that we're on right now. This is literally the next slide where we talk about hooks. So we will talk about hooks next. I know a lot of people have been curious about it. The idea is to determine what's called LDH. LDH is the development length of the hook, okay? And it is measured from the outermost face of the hook to however far the piece of bar is being embedded. There's only 2 types of hooks that we use. That's 90 degree and 180 degree. Those are the bend dimensions that are used according to whatever bar size that you have. But the formula is actually a lot simpler. Some parameters matter, some don't. Okay, so for instance, let's say the confinement or the temperature or the bar size factor or the top bar location factor, they actually don't really matter when you're dealing with hooks because you've changed the geometry of the problem. They don't really matter. The bar coding factor still does, but there's a couple new ones, a cover factor or a confinement factor. Because the geometry is different, you got to account for that. But in the end, it's another very similar equation. That's the LDH, or development length for hooks. That's all I've got. I will see you all on Friday. For a second there, I really wasn't, but we'll see you.